Hi guys, this is Math 148 and this is still section 10.4 and I wanted to go over question number 25, which is an inventory cost model problem. This is really similar to example 4 on page 687 and the problem reads this. A company needs 150,000 items per year. It costs the company $360 to prepare a production run, so maybe they're making templates or just having to get the ink or whatever they're doing, and $7 to produce each item. It also costs the company 75 cents per year for each item stored. So you have a cost for each production run and a cost to store each item. Find the number of items that should be produced in each production run so that the total cost of production and storage are minimized. So assume that you are making books or you're making necklaces or lunch boxes, and it costs, you're trying to decide, should you make them all at once, 150,000 items in one thing, but then it costs you money to store them, versus making production runs and reducing your storage costs. So here are the formulas you need to know, and again I'm following example 4. The trick to these is let X be the number of items for each production run. So you wouldn't necessarily know to do that, but I'm telling you, you let X be the number of items for each production run. Here's another formula. The total production cost is going to be the number of runs times the cost per run plus the number of items times the cost per item, which makes sense if you think that, well, your total cost for production is however many items you're making and the cost per item, and then you also have a cost for the production, which is the number of runs and the cost per run. That's sort of an overhead cost for each time you make a production run. And your total storage cost is the average number of items stored times the storage cost per item. Why do you go with an average number? Because the number is changing. If you have a little storage unit and you have all your lunch boxes or books stored there, you're not going to know the exact number, so you go with an average. And the average number stored is X divided by 2. How would you know this? Well, you might not. That's why I'm going over it. And there's a nice picture on page 678 that explains there's this kind of triangle as you're selling the items off. Then the average number is X over 2. So let's look at working this problem out. It's a long one. It'll probably take 3 pages of my little paint page. So question number 25. We're going to start by calculating the total production cost. So the production cost. So this is going to be the number of runs. Let me write this over here. X is going to be the items, the total number of items per production run. So the production cost, and again, if you look here, the production cost, we're going to do the total number of runs times the cost per run plus the number of items times the cost per item. So the total number of runs, this is tricky, is 150,000. That's the total number of items we need, divided by the number of items per run. That's the number of runs. If you think about it, you need 150,000 and you're making X for each run, so the number of runs is going to be 150,000 divided by X times cost per run is 360 plus the total number of items, again, total number of items, cost per item. Total number of items is 150,000, 1, 2, 3, because you need 150,000 for the whole year, times 7. That's the cost per item. See? Cost per item. So we had number of runs, cost per run, number of items, cost per item, excuse me, here, okay? So when you simplify this all out, you get 150,000 times 360 is, yes, that's a 5, 54 million, 1, 2, 3, that's 54 million. These have to be more excited commas and a better 5, divided by X, plus 150,000 times 7 is the easy breezy 1,050,000. These numbers are a little clunky to work with, but they're not, otherwise offensive. So now we have the production, now we need the storage. Why am I doing all this? Because I want the total cost, and the total cost is the production plus the storage cost. So this is how I have to do it. So we're going to do the average number stored times the storage cost per item, that's a T, item, So the average number stored is x divided by 2. And again, if you look on page 678, they have this nice little triangle. So for each storage run, you start with x, and at the end you have 0. So the average number that you had there is x divided by 2. So you can either think of this every time and work it out, or just think, well, the average number is x divided by 2 in a situation like this. And the storage per item is 75 cents. That is a 0.75. So the total here, 0.75 divided by 2 is 0.375 times x. 0.375 times x. So now we have our production cost and our storage cost. We can use the final formula, which is, I'll scroll down, total cost of production is the cost of production plus the cost of storage. So it's sort of redundant, but the total cost, I'm going to say C of x, is the cost of production, P, plus the cost of storage. So the cost of production is 54 million, 1, 2, 3, 1, 2, 3, all divided by x, plus 1050123, right? That's still the cost of production, little commas, plus the cost of storage, 0.375x. Big deep breath. I need a new page. So we have the total cost of production is 54 million divided by x plus 1,050,000 plus 0.375x. So that's the total cost of storage, production plus the total cost of storage. And we want to find the x that minimizes the cost, right? We want to find the minimum cost. So we're going to do this just like we did our other minimization problems from section 10.1. We're going to take the first derivative, and remember that this is x to the negative 1. So you can think of that as times x to the negative 1, like that. So our first derivative is minus 54 million, right? Because that's fun to work with. 54 million, all divided by x squared. Because when you take the derivative, it goes negative, and then you subtract 1, makes that x squared, negative 2, so like that. Plus the derivative of this piece is 0.375. And that's the derivative of that. So all of this is going to be equal when x squared is equal to 54. I'm just kind of making a little shortcut here, skipping a bit of a step, where that's divided by 0.375, like that. So this equals 0 when x equals 12,000. 1, 2, 3. So we're taking the square root, and we only want the positive side. So we don't worry about the negative 12,000, because you can't have a negative number of, you can't let x, which is the number of items you're making for each production run, that can't be negative. Cannot have negative items. So we want to check to make sure that this is a minimum cost. Check for minimum. And we can use our sign test, our first derivative sign test. We have 12,000, I'll say 12k, and we put, let's try a number on this side, 11,000, 11k. So if we put 11,000 into here, and again it's 11,000, so you have to plug in all the right zeros, into the first derivative, remember that's the first derivative, plug 11,000 into here, and you get minus 0.07. The number doesn't matter so much as the sign. We're saying the function is going negative on the left side, and then if we plug a number on this side of 12,000, let's say 13,000. So if you plug 13,000 into the first derivative, you get 0.0554. That number is positive. Again, I'm interested in more the sign of each number, not the actual value. So I see that my function goes down, then it hits a critical point at 12,000, then it goes back up again. Therefore, 12,000 is confirmed as a minimum. So now we are ready to answer our question. And at this point, I like to go back. It's helpful to just quickly check on the problem to see what they asked for. Find the number of items that should be produced. Okay, so all you have to do is find the number of items. You don't have to find the storage cost or anything. So our final answer is use 12,000 items. That's the end. 12,000 items for each storage run. for each production run, I should say. For each production, sorry, my handwriting looks really messy. Production run. And that is your answer. So you should be able to work a problem like this for the test. This is a long one. It would be worth more points because it's so long. And you need to show some of your work in here. So, good job. Difficult problem.